All right, guys, today we're going to talk about quadratic systems and inequalities. Now, this isn't going to go in our notes, but I do want to go over a couple of things here. So we've talked about systems before, and systems just mean that we have more than one equation, and we're trying to solve for kind of really where they intersect each other. So like, here's 3 quick examples of sort of the situations that could happen. So if I'm not dealing with 2 quadratics, if I have a quadratic, and I know so because of the squared thing, and then a line, because it doesn't have the squared thing, and they happen to look like this, then I can see that I have 2 solutions, right here and right here. And I can see where they are, because like this one here is at 4, 5. So what are the solutions? 4, 5, and this one here, which is at 0, -3. Same idea here. We got a parabola because it's squared, and then a horizontal line. And when I graph them, they only have one solution because they only touch one time. And again, I can find that solution because it's at -2, 5. And then finally, could have a parabola and a line that looks like this, and they don't touch at all. So 0 solutions. And there are none. So no. Now, these ones are just more graphing examples, but what you could also do is you could do it algebraically. So you could graph them and look for it, and sometimes I really like to do that, but sometimes I just like to do it algebraically. And so I'm just going to do these last 2 right here real quick because this one's a little trickier because it's in vertex form, so but you wouldn't have something like that necessarily. So the thing is, if I have 2 equations equal to y, then they are equal to each other. Basically, we're solving by substitution here. It's kind of what you want to do. Elimination doesn't work so much because you have an x squared, and then in your other equation, you don't. So you just want to really make them both equal to y, and then make them equal to each other. Now, overall, right now, this problem is just a quadratic like what we have been doing. And so if I want to solve it, I want to make it equal to 0. And so we'd have x squared minus 2x plus 2. And we could try to factor that, but I think it would be a bad time. So since we are in standard form, I'm just going to use the quadratic formula. So we'll have -b plus or minus the square root of b squared minus 4 times a, which is 1, so I don't need it, times c, which is 2, all over 2a, so just 2. So I think we're going to have x equals 2 plus or minus the square root of 4 minus 8, all over 2. So it's looking like we are going to get some imaginary solutions here, which I do. I think we end up with 2 plus or minus 2i over 2, or really 1 plus or minus 1i. And since my answers are imaginary, that kind of means we have a situation like this one. Again, if I think about graphing this, we have a horizontal line at -5. And then this graph is going to have a vertex. So to find the vertex in standard form, we have to do -b over 2a. So it'll be at 1 comma something. And to find that something, we want to plug it in. So we're going to have 1 minus 2 minus 3, which is -4. And then my parabola has a slope of 1. So yeah, like that parabola is just missing that line there. They are not going to touch, so they don't have any solutions. And again, I could kind of tell when I was solving here because the solutions were imaginary. Now, an example of something that doesn't have imaginary solutions, I think, I hope, this one here. So again, if I wanted to solve by substitution, that would really work because both these equations are equal to y. So I can set them equal to each other. And then once I do that, it's not really a parabola and a line anymore. We're just solving a quadratic because there's an x squared involved. And so whenever we're solving a quadratic, we're going to want it to be equal to 0. So I would actually add the x squared over to keep it positive. subtract the 2x, and subtract the 7. So we're going to have x squared minus 4x minus 5. Ooh, and that might actually factor. Because if I think about what multiplies to negative 5 and adds to negative 4, I think I could do x minus 5 and then x plus 1. Like that one multiply up to negative 5 and add up to negative 4. And so in factored form, it's actually really easy to solve. My two solutions are 5 and negative 1. However, I'm kind of only half done because if you remember up here, my solutions were like ordered pairs, like x comma y. And really right now, all I've found is x. So I kind of have to go back and plug it in for x to find y. So I'm going to do that in the bottom equation because it's easier. So we'll have like negative 2 times 5 plus 2. So negative 10 plus 2 for negative 8. And then my other x value of negative 1, if we plug that in, we'll have negative 2 times negative 1 plus 2. So 2 plus 2, so 4. So let's just graph it a little and see if that makes sense. So like up here, again, we have a quadratic in standard form. So if I want to graph that, I need to find the vertex by doing negative b over 2a. So at 1 again. And then I got to plug her in. So 1 squared is 1, but then there's a negative. 2 times 1 is 2. And then plus 7. So we're looking at 1 comma 8 here. Then it's got a slope of negative 1. So kind of like that. And that's really all I can get because that's also my y-intercept. We could plug in other values, but maybe we won't. Let's just graph this line. So this is a line in y equals mx plus b. So my y-intercept is at 2. And then we're doing a slope of down 2 over 1. And so we get this line here. And we have our parabola here. So this isn't the best sketch of a parabola because I am sort of estimating how big it's getting. But if we kind of think about our answers, we had 5 comma negative 8 for one of them. So if I go to like 5, negative 8, that's like totally believable. Mine's a sketch, so it's not exactly there, but that makes sense. Like that's generally the location where they're going to intersect each other. And then the other one at negative 1 comma 4, that looks real good actually. So my graph is off because I'm sketching my parabola because I didn't plot a lot of points. But it seems like I'm on the right track here. So, okay, now another thing we are going to talk about and put in our notebook. Now, I mean, this is all well and good. I think we kind of understand this, but something that we haven't talked about a ton are quadratic inequalities or just like graphing inequalities in general. So when I don't have an equal sign in my equation, but I want to graph it, like inequalities are less than, greater than, less than or equal to, greater than or equal to. If we have to graph those, you kind of have to graph them a little bit differently. Like you have to take your time and really think about your line. So if you are less than or greater than, you are going to have to make a dashed line or like a dashed parabola. If it is equal to, so like these go here, then you're going to be a solid line or solid parabola. You'll shade up whenever you're greater than or equal to. And kind of what's interesting is like if you're a parabola and you're like pointing up and shading up, you're really kind of inside. But if you're a parabola pointing down and you're shading up, then it's kind of like everything outside. And then shading down is less than. And if you're a parabola pointing up, that's going to be like everything outside. But if you're a parabola pointing down and you're shading down, that's everything inside. So like down and down, inside. And then up and up is inside. So that's kind of a good way to remember it, I think. So for any system of inequalities, be it quadratic, lines, whatever, any point that lies within the double shaded area or on a solid boundary line is a solution of that. And the reason I say double is because, if we're talking about systems, we have more than one thing. And so we're going to be shading twice. And so wherever you did shade twice, that's your answer. If you only shaded an area once, that's not really part of your answer because it has to apply to both things. So let's try a couple. All right, so we're going to graph some quadratics here, which that's real good because we're going to have to do that on our test soon. So here we are in standard form. So we're going to find that vertex by doing negative b over 2a and then plug it in. So negative 2 over 2 times negative 1. So we're looking at 1 comma something. When I plug the 1 in, 1 squared is 1 with a negative is negative 1. 1 times 2 is 2 plus 1, so all that is 2. And then when I'm in standard form, the y-intercept is really easy to find. It's just that last number there. So we can plot our vertex. We can do our slope, which also happens to get me my y-intercept. And when I go to draw my parabola now, I have to be careful because it's not equal to, it's greater than. Because it's not equal to, we have to do a dashed line or a dashed parabola. And because we're going to be greater than this, we have to be above all of it. Okay, now this isn't a system, this is just one. So looking at this one here, we are already in vertex form, so my vertex is easy to find. It's 2 comma negative 3. So 2 comma negative 3. We can do our slope of up 2 over 1. We could also get our y-intercept by plugging in 0. So we'll get 4 times 2 is 8 minus 3, so 5. And we can flip that over and put it on the other side. Then when I go to draw my parabola, because I'm equal to, I actually can do a solid filled in parabola now. My goodness, I'm hitting my fold line under there. And now we're less. So less is going to be under. And so under this parabola is kind of all the stuff outside of it. And then last but not least, we have a parabola in intercept form or factored form. My goodness. So that means these are my x-intercepts, but opposite. So 3 comma 0 and negative 1 comma 0. Then we can find the vertex, or at least the axis of symmetry, by boop, boop, booping into the middle. So that's at 1 comma something. And to figure out that something, we just want to plug it in. It's like 1 minus 3 times 1 plus 1. So negative 2 times 2. And that's the thing that should always happen. Like when you're finding the vertex in factored form, these two numbers in parentheses should be opposite numbers. So same but different signs. So negative 4. Now when I think about sketching out the parabola, I can do a solid line because we are equal to. Oop, I could have done my slope to get it slightly better there, but that's all right. And then we're greater than, and this is an up parabola, and greater than means all this stuff inside the parabola. So I didn't find the y-intercept, but whatever. Okay. Now these ones are already graphed for us. We just have to shade, or at least this first one is. We just have to shade. So this one is definitely talking about the parabola, and I can tell because it's squared. Also because it's equal to, and the other one's not. And it wants to be less. So less than this parabola is kind of below, and so that's going to be all this stuff outside. And notice that I'm doing it pretty light because we're going to shade two things. And so wherever I double shade, that's actually the solution. Now the other one is a line, and I know so because there's no squared. And then I also know it's the line because it's dashed and it's not equal to. And we want to shade above because we're greater. So above the line is all this stuff. Now, I'm not going to go inside the parabola because I already know I can't be in there. So I think it's really just going to be like this little part up here and then this little part over here that we shade. And so then, like, if I gave you a point like 7, 1, if I go over 7 up 1, that is a solution. If I give you a point like 2, -4, that is not a solution because it's not in the shaded area. Okay. Looking at this next one here, this first one I can tell is a parabola because it's squared in vertex form. So we're at -3, -2. Got a slope of 1, and it's going to be solid because we're equal to. So we're kind of looking like this. We also want to shade above, and so that's going to be all this stuff inside, but I'm not going to shade too dark because I do have another thing to graph. And actually, the other thing that I have to graph is a V. That's an absolute value because it's got those bars, and those are always V-shaped. They are very similar to vertex form parabolas because -3, 4 is your vertex. 1, 2, 3, 4. The only difference being, like, so at a parabola, I can only do my slope once. A V is lines on either side, so I can do the slope of -1 as many times as I want. Oh, yep, solid line. Shoot, that was almost a bad time, but it is a solid line, so that's good. But yeah, I can do my slope as many times as I want because a V has lines on either side. And then this V is shaded below, although I shouldn't have gone out there because the parabola said I couldn't be out there. So I think we're just going to be all this stuff right in here. That's cute. That's fun. Okay. So anything in here is a solution. Anything anywhere else is not. And so then that's kind of where we can maybe go backwards. And so looking at this last one, I notice I have a parabola and they're showing me the vertex. So I'm totally going to write that in vertex form. Now I'm not going to put my inequality because I'm not sure yet, but we're going to have like x minus 2 squared minus 3. Definitely seems like my slope is 1, so I'm going to leave it 1. And then because it's solid, we're equal to, and because we didn't shade inside, like I think we shaded below, below this parabola, so that's less. Now the other thing that I have here is a line, like a y equals mx plus b thing probably. I can see that my y-intercept is 1, so I'll have like +1 at the end. And then to find my slope, I can just count to the next nice crosshair point. So I think like down 1/2 looks real good for my slope. And then that's a dashed line, so I'm not going to make it equal to. And we did shade below that line, so less. Hopefully that's kind of okay. Looking at this one here, we got 2 parabolas. So I'm going to start with the one with the solid line. So I know that we're equal to. Has a vertex again, so I'm going to go vertex form like x minus 2 squared minus 3. Slope of 1 again, so that's all set. And they sort of shaded above that parabola, so greater. The other parabola is not equal to, so we're not going to put the little equal to line. I can see the vertex again, so we're doing x minus 4 squared plus 4, JK, plus 4. Oh, well, sorry. Slope of, -1 this time because we are pointing down. And again, it looks like they shaded below that, so we're going less. And then last but not least, we got a parabola. So let's start with that one. On my parabola, it is not equal to because we're a dashed line, but it does seem like we've shaded above it, so greater. I can see my vertex again, so we'll do vertex form, so like x minus 2 squared minus 3 with a slope of +1. Thank goodness I didn't have to squeeze a negative sign in there. Now my other graph is a V graph, so that's going to be like an absolute value situation. We're going to take our vertex, so 2 and 4, and put like x minus 2 plus 4. And this graph is equal to, so we'll have the equal to line. Seems like we shaded below, so less. Easy, easy, hopefully. There's something on the back that we can't see. But I'll show you actually real quick. Is each one a solution? We kind of talked about that a little bit. I know you can't do this on here, but like you can watch and learn. So solution must satisfy all inequalities. So I just like to graph them and kind of see. So like if we go to 3, negative 2, that's not in both. So that is not a solution. 1, negative 3, not in both. It's not even on a solid line, so definitely not. 2, 3, that is in the double shaded region, so that is a solution. And then 1, 6 would totally be in there. I can't see it, but I know it is. So, all right, there we go. We learned all the things.